70,000 years ago, while our ancestors huddled around fires on the African savanna, while they chipped stone tools and painted ochre on cave walls, something passed through the outer edges of our solar system. It came closer than any known star has ever come. It drifted through a region we now call the Oort Cloud, that vast frozen shell of comets and ice that surrounds our sun like a ghostly halo, and no one knew, no one could have known. The humans alive at that time had no telescopes, no mathematics, no written language. They looked up at the same sky we look up at tonight, and they saw nothing unusual. The visitor was too faint, too dim, too small. It slipped past us in the dark, a cosmic intruder brushing against the outermost boundary of our home, and then it vanished into the black. That visitor was a star. A real star with a companion, a binary system consisting of a small red dwarf and an even smaller brown dwarf, bound together in a slow, quiet orbit around their common center of mass. Today we call it Scholz's star, named after the German astronomer Ralph Dieter Scholz, who first identified it in 2013. And when astronomers traced its motion backward through time, they discovered something that sent a chill through the astrophysics community. This star had passed within 0.82 light-years of our Sun. Some estimates place it even closer, perhaps as near as 0.6 light-years. To put that in perspective, the nearest star to us right now, Proxima Centauri, sits 4.2 light-years away. Scholz's star came more than 5 times closer than our current nearest neighbor. It entered territory that, by any reasonable definition, belongs to our solar system. And here is what makes this discovery so deeply unsettling. This was not a 1 in a billion event. This was not some extraordinary coincidence, some cosmic anomaly that happened once and will never happen again. Astronomers now believe that stellar flybys like this one happen far more often than we once assumed. Statistical models suggest that a star passes within 1 light-year of our Sun roughly once every 100,000 years. Some calculations put it even more frequently than that. That means in the 4.6 billion year history of our solar system, tens of thousands of stars may have wandered this close. Some of them may have come much closer. Some of them may have disrupted comets, nudged orbits, scattered debris inward toward the inner planets, toward Earth. The question is not whether our solar system has been visited. The question is what those visits have done to us, and what they might yet do. Think about what that means. We tend to imagine our solar system as a stable, orderly place, the sun at the center, the planets tracing their predictable ellipses, everything humming along in gravitational harmony as it has for billions of years. But that picture is incomplete. Our solar system is not a sealed room. It is an open house in a crowded neighborhood, and the neighborhood is in constant motion. Stars drift, orbits shift. Gravitational threads connect us to passing objects we never see, never detect, never suspect. Scholz's star is simply the first visitor we have been able to identify with confidence. It will not be the last. We are going to trace the full arc of this story tonight. We are going to follow the path of a dim, quiet star as it wandered through our Oort Cloud at a time when our species was young and unaware. We are going to examine what it may have done to the frozen bodies it encountered, and what those disturbed bodies might mean for the future of our planet. We are going to look outward, past the planets, past the Kuiper Belt, into the vast sphere of ice and silence that marks the true border of our Sun's domain. And we are going to confront a truth that astronomers are only now beginning to fully appreciate, that our solar system has never been as safe as it looks, that the ground we stand on is not as solid as we believe, that the calm we feel when we look up at the stars is in some fundamental sense an illusion born of our inability to perceive the slowness of cosmic time. By the end of tonight, you're going to understand what Scholz's star was, how close it really came, what it may have done to the comets and objects in our outer solar system, and why this single discovery has forced astronomers to rethink the stability of our cosmic home. You are going to see our solar system not as a fortress, but as a raft on an open ocean, exposed, vulnerable, and shaped by forces that arrive without warning and leave without a trace. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why Scholz's star matters, we first need to understand the architecture of the space we live in. Not just the planets, not just the Sun, but the full extent of the territory our solar system claims, and how fragile that territory really is. Because the story of Scholz's star is not just a story about a single stellar encounter. It is a story about the shape of our home and about the forces that have been quietly reshaping it for billions of years. The Sun sits at the center. It is a medium-sized star, a ball of hydrogen and helium, roughly 864,000 miles across. If you could line up Earths side by side, you would need 109 of them to span the Sun's diameter. It contains 99.86% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, every ring particle, every grain of dust, accounts for the remaining fraction of a percent. The Sun's gravity dominates this space utterly. It reaches outward in every direction, thinning with distance according to the inverse square law, but never truly vanishing, pulling on objects trillions of miles away with a grip so faint it can barely be measured, yet so persistent that it shapes the trajectories of ice and rock for millions upon millions of years. The inner solar system is the part most of us know. Mercury, the smallest planet, baked and cratered, orbiting just 36 million miles from the Sun. Venus, shrouded in dense clouds of sulfuric acid, its surface hot enough to melt lead. Earth, our home, orbiting at the convenient distance of about 93 million miles. Mars, the red desert, cold and thin-aired, with dust storms that can envelop the entire planet. And between Mars and Jupiter, the asteroid belt, a broad ring of rocky debris left over from the formation of the solar system, containing millions of objects ranging in size from dust grains to the dwarf planet Ceres, which is roughly 590 miles across. Then comes the outer solar system, the domain of the giants. Jupiter, the king, a gas giant with a mass more than 300 times that of Earth, orbiting at about 484 million miles from the Sun. Saturn, the ringed wonder, roughly 886 million miles out. Uranus, tipped on its side, orbiting at about 1.8 billion miles. Neptune, the outermost known planet, circles the Sun at an average distance of roughly 2.8 billion miles. That seems vast. It is vast. A beam of light, traveling at 186,000 miles per second, takes over 4 hours to reach Neptune from the Sun. But in the full picture of the solar system, Neptune is still close. It is still well within the Sun's firm gravitational embrace. It is, in a sense, still sitting in the Sun's living room. Beyond Neptune lies the Kuiper Belt, a region of frozen bodies extending from about 30 astronomical units to roughly 50 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So the Kuiper Belt stretches from roughly 2.8 billion miles to about 4.6 billion miles out. This is where Pluto lives, demoted from planetary status in 2006 by the International Astronomical Union, but still orbiting faithfully in its elongated, tilted orbit. This is where we find Eris, discovered in 2005 by astronomer Mike Brown and his team at Caltech, a body so similar in size to Pluto that its discovery forced the reclassification debate. Make, Haumea, and thousands of other icy worlds populate this region, too small and too distant to see without powerful telescopes. The Kuiper Belt is often described as the solar system's attic, cold, cluttered, and full of relics from the time of planetary formation 4.5 billion years ago. The New Horizons spacecraft, launched in 2006, flew past Pluto in 2015 and continued on to visit the Kuiper Belt object Arrokoth, formerly known as Ultima Thule, in 2019, giving us our first close-up look at one of these frozen, pristine remnants. But even the Kuiper Belt is not the edge. Beyond it, the Sun's influence continues, far, far beyond, into a realm of cold and darkness that challenges the imagination. Stretching outward from roughly 2,000 astronomical units to perhaps 100,000 astronomical units, there exists a hypothetical shell of icy objects called the Oort Cloud. This structure, first proposed by the Dutch astronomer Jan Hendrik Oort in 1950, is believed to contain billions, perhaps trillions, of comets and frozen bodies. No one has ever directly observed the Oort Cloud. No telescope has imaged it. No spacecraft has reached it. and none will for centuries. We infer its existence from the orbits of long-period comets, those comets that arrive from all directions, on orbits that take thousands or even millions of years to complete. Something must be sending them inward. Something must exist out there in the deep cold, waiting. The Oort Cloud is, in the truest sense, the largest structure associated with our Sun, and also the most mysterious. Now here is where scale becomes important, and where the human mind begins to struggle. We evolved to understand distances measured in footsteps and throwing ranges, not in trillions of miles. So let us use comparisons that bring these numbers closer to human experience. If we shrank the Sun down to the size of a basketball, about 9.5 inches across, Earth would be a small pea, roughly 1 millimeter in diameter, orbiting about 26 meters away. That is about 85 feet, roughly the length of a tennis court. Jupiter would be a walnut, about 1 centimeter across, sitting roughly 135 meters from the basketball, more than a city block away. Neptune, the last known planet, would be a blueberry sitting almost half a kilometer from the basketball, about a quarter mile out. And the Oort Cloud? That frozen shell of comets would extend outward to a distance of roughly 7 to 15 kilometers from the basketball. Imagine standing in a city park, holding a basketball in your hands, and knowing that the outermost edge of your domain, the farthest objects gravitationally bound to you, sits somewhere across town, invisible, undetectable, scattered in every direction like grains of sand tossed by the wind. That is the scale of our solar system, and that is the territory Scholz's star entered. Let us be precise about the distances, because precision matters in this story. Scholz's star passed within roughly 0.82 light-years of the Sun. 1 light-year is about 5.88 trillion miles, or roughly 63,241 astronomical units. So 0.82 light-years is approximately 51,858 astronomical units, or about 4.82 trillion miles. The outer boundary of the Oort Cloud is estimated to lie at about 100,000 astronomical units, or roughly 1.6 light-years. This means Scholz's star did not merely approach our solar system from outside. It entered it. It crossed the boundary. It moved among the frozen comets and ice fragments that orbit our Sun at the farthest reaches of its gravitational influence. If you were to drive a car at highway speed, say 60 miles per hour, from Earth to where Scholz's star made its closest approach, the drive would take roughly 58 million years. You could listen to every song ever recorded, every podcast, every audiobook, millions of times over, and you would still not be halfway there. At the speed of light, the fastest speed anything can travel in this universe, the journey would take just under 10 months. Light from our Sun, streaming outward at 186,000 miles per second, would need almost a year to reach the point where Scholz's star crossed our threshold. That is simultaneously very close, by the standards of interstellar space, and unimaginably far by any human measure. The human mind is not built for these scales. We evolved to navigate savannas and forests, to judge the distance to a watering hole or the speed of a predator charging through tall grass. The cosmos does not operate on our terms. It never has. Here is another way to grasp the distance. If the entire solar system, from the Sun out to the edge of the Oort Cloud, were compressed to the size of a standard football field, 100 yards from goal line to goal line, the Sun would be a microscopic dot on one goal line. Earth would be invisible without magnification, sitting less than a millimeter from the dot. Neptune would be roughly 2 centimeters out, not even an inch, and the Oort Cloud would fill the rest of the field, stretching all the way to the far end zone, a thin haze of frozen objects spread across the full length of the pitch. In this model, Scholz's star would have entered the field at approximately the 50-yard line. It got halfway in. This was not a near miss. This was not a close call in any reassuring sense. This was an intrusion. The visitor crossed our border and walked through our outermost territories. The story of how we found Scholz's star begins with careful observation, painstaking data analysis, and a fair amount of serendipity. In 2013, Ralph Dieter Scholz, astronomer working at the Leibniz Institute for Astrophysics in Potsdam, Germany, identified a previously untallowed star, while examining data from the WISE satellite, the Wide Field Infrared Survey Explorer, and the 2-micron all-sky survey, known as 2MASS. It was dim, extremely dim. It was a red dwarf, the most common type of star in the galaxy, and one of the faintest. Red dwarfs are small stars with surface temperatures far cooler than the Sun, typically between 2000 and 3500 Kelvin, compared to the Sun's 5800 Kelvin. They glow at only a fraction of the Sun's luminosity, often less than 1%, emitting most of their radiation in the infrared, invisible to human eyes. This particular red dwarf had a companion, a brown dwarf, an object even smaller and dimmer, too small to sustain hydrogen fusion in its core, sometimes called a failed star. Together, this binary system was so faint that it had escaped detection for all of recorded astronomical history. It was lurking less than 20 light-years from the Sun, and nobody had noticed it. What caught attention was not its brightness but its motion. Every star in the sky moves, the Sun moves, the entire galaxy rotates, but most stars appear nearly stationary to us because they are so far away that their motion across the sky, known as their proper motion, is imperceptible over a human lifetime. Scholz's star had a peculiar motion profile. Its proper motion across the sky was very small, but its radial velocity, its speed toward or away from us along our line of sight, was large. It was moving almost directly away from the Sun. This combination was unusual and immediately interesting. A star moving almost radially, with very little sideways drift, is either coming straight toward us or moving straight away from us. Scholz's star was receding. It was getting farther from us with every passing year. And that raised an immediate and electrifying question. If it is moving away now, where was it before? How close did it once come? In 2015, a team led by astronomer Eric Mamajek at the University of Rochester published a landmark paper in the astrophysical journal Letters that answered that question with startling precision. Using data from multiple sources, including proper motion measurements from the WISE and 2MASS surveys, radial velocity readings from the Magellan telescopes at Las Campanas Observatory in Chile, and distance estimates derived from trigonometric parallax, the team traced the trajectory of Scholz's star backward through time. The orbital mechanics were straightforward, but required painstaking attention to uncertainties. The calculations converged on a single, remarkable conclusion. Approximately 70,000 years ago, give or take a few thousand years, Scholz's star passed through the outer Oort Cloud at a distance of roughly 0.82 light-years from the Sun. With 98% confidence, the closest approach was within 1.2 light-years. The most likely value was 0.82. Some subsequent analyses, incorporating additional data and refined mass estimates, have suggested even closer passages, perhaps as near as 0.6 light-years, though these estimates carry larger uncertainties. To put the mass and luminosity of this system into perspective, consider how different Scholz's star is from the stars we see in the night sky. The brightest star visible from Earth, Sirius, has a luminosity roughly 25 times that of the Sun. It blazes in the constellation Canis Major at a distance of about 8.6 light-years, visible to the naked eye across millennia of human history, a fixture in the mythologies of ancient Egypt, Greece, and Rome. Scholz's star, at its closest approach, was less than 1/10 of that distance from us, and yet it was utterly invisible. Its combined luminosity, both the red dwarf and the brown dwarf together, is less than 1/2000th of 1% of the Sun's output. If you were standing on a hypothetical planet orbiting Scholz's star, the Sun would appear as a moderately bright star in your sky, unremarkable among the thousands visible to the naked eye. The asymmetry is striking. We can see the Sun from Scholz's star's current location, but from Earth, even at closest approach, Scholz's star was a ghost. It required the most sensitive infrared instruments humanity has ever built to detect it at all, and even then it was spotted almost by accident, a faint smudge on a digital survey image that an astronomer happened to examine at the right time. The brown dwarf companion deserves particular attention because it represents a category of object that challenges our assumptions about what a star is. Brown dwarfs occupy an awkward middle ground between planets and stars. They form the way stars do, from the gravitational collapse of gas clouds, but they never accumulate enough mass to ignite sustained hydrogen fusion in their cores. The threshold for hydrogen fusion is roughly 80 Jupiter masses, or about 7.5% of the Sun's mass. Below that threshold, a collapsing ball of gas will heat up, glow dimly for a time, but never achieve the self-sustaining nuclear reactions that define a true star. Scholz's star's companion, at roughly 65 Jupiter masses, falls well below this threshold. It is a T-type brown dwarf, meaning its surface temperature is below roughly 1400 Kelvin, cooler than many industrial furnaces, cooler than the filament of an incandescent light bulb. It glows in the infrared with a luminosity so feeble that it contributes almost nothing to the system's already meager light output. In a very real sense, this binary system that invaded our solar system consists of a barely a star and a not quite a star. It is the cosmic equivalent of two shadows passing through a dark room. And yet, despite its faintness, this system carries mass. Not much mass, by stellar standards, but enough to exert a gravitational influence on everything it passes near. Gravity does not care about luminosity. Gravity does not care whether an object glows or is dark, whether it is visible or invisible, whether it is a blazing supergiant or a frozen brown dwarf tumbling through the void. Gravity responds only to mass, and mass is what Scholz's star brought with it when it entered our Oort cloud. The total gravitational pull of the binary system, acting on the comets and ice fragments at the outer edge of our solar system, was equivalent to roughly 9% of the Sun's pull at that same distance. 9% does not sound like much. But at the outer edge of the Oort cloud, where the Sun's own gravity is already desperately weak, 9% of a small number can be enough to make a difference. It can be enough to tip the balance for objects already teetering on the edge of gravitational escape. There is an additional detail about the discovery that reveals something important about the state of our astronomical knowledge. Scholz's star was located less than 20 light-years from the Sun when it was finally identified in 2013. 20 light-years is an extraordinarily small distance by astronomical standards. It is well within what astronomers call the solar neighborhood, the region of space close enough to the Sun that individual stars can be studied in detail. And yet this star, this binary system, had been missed by every survey, every catalogue, every sky search conducted in the entire history of astronomy. It was hiding in plain sight, or rather, hiding in plain darkness, too faint to trigger the detection algorithms of surveys designed to find brighter objects, too red to appear on photographic plates optimized for visible light, too slow-moving across the sky to attract the attention of proper motion surveys that flagged fast-moving stars as nearby candidates. It was, in a sense, the perfect infiltrator, possessing exactly the combination of properties needed to evade every astronomical dragnet humanity had deployed. This raises an unsettling question. If we missed a star this close for this long, what else are we missing? How many other faint, cool, dim objects are drifting through the solar neighborhood, undetected and uncatalogued? The answer, based on statistical models of the stellar population, is probably quite a few. Brown dwarfs are believed to be extremely common, possibly as numerous as main sequence stars, and the faintest of them can only be detected at very short distances. The WISE survey, which discovered Scholz's star, has identified hundreds of previously unknown brown dwarfs in the solar neighborhood. But the survey has sensitivity limits, and objects below those limits remain invisible. For every Scholz's star we have found, there may be several more lurking nearby, too faint to see, their trajectories unknown, their future paths through our neighborhood uncharted. The paper was titled "The Closest Known Flyby of a Star to the Solar System," and it attracted immediate and widespread attention, both within the astronomical community and in the broader public sphere. The discovery was significant not because of what Scholz's star did in any immediate, destructive sense. Nothing dramatic happened. No comet was observed to arrive. No planet was perturbed. The inner solar system continued on its way, oblivious. The significance lay in what the discovery proved was possible. Here was concrete, observational evidence that stars can and do pass through our solar system's outermost territories. Here was proof that our home is not isolated. The Oort cloud, that fragile reservoir of ancient ice, is not a sealed vault. It is exposed. It has been visited before. It will be visited again. And the timing matters. 70,000 years is not a long time in cosmic terms. It is barely a heartbeat. The Earth is 4.54 billion years old. 70,000 years represents less than 0.002% of Earth's history. If you compress the entire age of the Earth into a single 24-hour day, 70,000 years would be about 1.3 seconds. That is how recently this happened. On the grand clock of Earth's existence, Scholz's star passed through our solar system roughly 1 second ago. It practically just happened. The comets it may have disturbed could still be falling inward right now, drifting toward the inner solar system on orbits that take millions of years to complete. The consequences of this visit, if any, may not have arrived yet. They may still be en route, crawling sunward through the dark, invisible, and patient. One more scaled comparison to anchor this in human experience. Imagine the entire history of the Earth compressed into a single calendar year. The planet forms on January 1st. The first simple cells appear in late March. Complex multicellular life does not emerge until late October. The dinosaurs arrive around December 14th. They go extinct on December 26th. All of human evolution, from the first hominids to the present day, occupies the final hours of December 31st. All of recorded civilization, every city, every empire, every war, every poem, every equation, every cathedral, every spacecraft, fits into the last few seconds before midnight. In this compressed timeline, Scholz's star would have passed by roughly half a second ago. It is that recent. It is that close to the present moment. The discovery also raised a question with far broader and more troubling implications. If we found one star that passed this close this recently, how many others have there been? The Milky Way galaxy contains between 100 billion and 400 billion stars. They are all moving. They are all tracing complex orbits around the galactic center, and those orbits carry them through one another's neighborhoods on time scales measured in millions of years. The galaxy is not a static collection of fixed points. It is a river of stars, flowing, mixing, constantly rearranging itself. Scholz's star is not special. It is simply the first one we caught in the act, or rather, the first one we caught leaving the scene. The galaxy is full of wanderers, and some of them have undoubtedly come closer than Scholz's star did. Some of them, statistically speaking, must have come much, much closer. But what scientists discovered next was worse than anyone expected. The core problem is not Scholz's star itself. Scholz's star was small, faint, and fast-moving. Its passage through the Oort Cloud was, in the grand scheme of cosmic events, relatively gentle, more a brush than a blow. The core problem is what Scholz's star represents, a window into a kind of violence that lurks permanently at the edges of our seemingly peaceful solar system. A violence that is slow, invisible, and patient, operating on timescales so vast that no human civilization has ever witnessed its full consequences, but no less real for being subtle, no less dangerous for being slow. For decades, astronomers have known that the Oort Cloud exists in a state of delicate gravitational balance. The comets and ice fragments that populate it are bound to the Sun, yes, but only barely. They orbit at such extreme distances that the Sun's gravitational pull on them is almost negligible. To understand how weak this grip truly is, consider that the force of gravity decreases with the square of the distance. An object at 100,000 astronomical units from the Sun experiences a gravitational pull roughly 10 billion times weaker than what we feel on the surface of the Earth. A person standing at that distance would weigh effectively nothing in the Sun's gravitational field. The comets that orbit there are held in place not by a firm grip, but by the faintest possible whisper of attraction, the ghost of a force, barely distinguishable from nothing at all, and a small nudge, a slight gravitational tug from a passing star, from a dense molecular cloud, from the tidal forces of the galaxy itself, can be enough to break that whisper and send those comets drifting off their ancient paths. And once dislodged, those comets begin to fall. They fall inward, toward the Sun, on long, sweeping trajectories that can take hundreds of thousands or even millions of years to complete. Their orbits are highly elliptical, enormous elongated loops that plunge from the outer darkness into the bright inner sanctum of the solar system, and then, if they survive the journey, swing back out again into the cold. Some of them cross the orbits of the outer planets. Some of them cross the orbits of the inner planets. Some of them cross the orbit of Earth. And some of them, on very rare but statistically inevitable occasions, do not merely cross the orbit of Earth, but arrive at the same point in that orbit at the same moment that Earth itself is there. When that happens, it is called an impact, and impacts, even rare ones, can change the course of life on a planet. This is the comet shower hypothesis. It was first proposed in detail in the early 1980s, drawing on theoretical work by astronomers including Jack Hills, who in 1981 described how a passing star could inject comets from the Oort Cloud into the inner solar system. The idea has been refined many times since, incorporating better models of the Oort Cloud structure, improved simulations of gravitational dynamics, and increasingly precise data on the orbits of known comets. The concept is straightforward in principle, though fiendishly complex in detail. When a star passes close to the Sun, it gravitationally perturbs the Oort Cloud. It does not need to come anywhere near Earth. It does not need to enter the inner solar system. It merely needs to tug on the outermost comets, shifting their orbits just enough to send some of them sunward. Because the Oort Cloud is believed to contain trillions of objects, even a tiny perturbation affecting a small fraction of them can dislodge millions of comets. Most of those comets will miss Earth entirely. They will sail through the inner solar system on paths that pass nowhere near our planet, or they will be gravitationally captured or deflected by Jupiter, the solar system's great protector, whose enormous mass acts as a shield, sweeping up or ejecting many of the dangerous objects that venture inward. Others will fall directly into the Sun and be vaporized, but some of them, a small and statistically unavoidable fraction, will cross Earth's orbit at exactly the wrong time. And when a comet strikes a planet, the consequences can be catastrophic beyond anything in normal human experience, beyond anything we have words for. We know this because it has happened before. The evidence is written in the rocks. 66 million years ago, an object roughly 10 kilometers across, perhaps 6 miles in diameter, struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater and triggering a mass extinction that wiped out approximately 75% of all species on Earth, including all non-avian dinosaurs. The impactor, whatever it was, arrived at a speed of roughly 20 kilometers per second, about 45,000 miles per hour. It punched through the atmosphere in less than a second. When it struck the surface, it released energy equivalent to roughly 10 billion Hiroshima bombs, an almost meaningless number that translates into physical effects we can barely imagine. The blast created a hole in the Earth's crust roughly 180 kilometers wide and 20 kilometers deep. It generated tsunamis hundreds of meters tall that swept across the Gulf of Mexico and beyond. It ejected billions of tons of rock, dust, and sulfur-rich debris into the atmosphere, creating a global pole that blocked sunlight for months or possibly years, collapsing food chains, killing plants, starving herbivores, starving the carnivores that fed on them, and plunging the planet into a prolonged winter from which most large animals never recovered. The entire biosphere was reshaped in a geological instant. The nature of the Chicxulub impactor, whether it was an asteroid from the main belt between Mars and Jupiter or a comet from the outer solar system, remains debated among researchers. A 2021 study published in the journal Scientific Reports by Avi Loeb and Amir Siraj at Harvard University proposed that the impactor may have been a fragment of a long-period comet dislodged from the Oort cloud by Jupiter's gravity. Other researchers dispute this conclusion, favoring an asteroidal origin based on the chemical composition of the impact debris. The debate is ongoing and may not be settled definitively, but the mechanism is clear and undeniable regardless of the impactor's origin. Objects from space can hit Earth, and when they do, they can end worlds. The question raised by Scholz's star is whether stellar flybys play a role in triggering these events, whether the extinction record, our planet's long and terrible history of mass dying, is partly written in the orbits of passing stars that no one has ever observed. Whether there is a connection, however tenuous, between a dim red dwarf drifting through the Oort cloud and a wall of flame sweeping across a continent millions of years later. This question matters because the Chicxulub impact was not unique. It was merely the most recent large-scale impact event we have studied in detail. The geological record preserves evidence of dozens of significant impacts stretching back billions of years. The Vredefort crater in South Africa, roughly 2 billion years old and originally about 300 kilometers in diameter, is the largest confirmed impact structure on Earth. The Sudbury Basin in Ontario, Canada, formed by an impact roughly 1.85 billion years ago, is the second largest. The Popigai crater in Siberia, about 36 million years old, and the Chesapeake Bay crater on the eastern coast of the United States, about the same age, record a pair of large impacts that occurred within a few 100,000 years of each other, possibly suggesting a period of elevated bombardment. The Late Heavy Bombardment, a hypothesized period of intense asteroid and comet impacts roughly 4 billion years ago, may have sterilized Earth's surface multiple times before life gained a permanent foothold. Impact events are not rare when measured on geological timescales. They are a recurring feature of Earth's history, as natural and as inevitable as volcanic eruptions or ice ages, and they are driven, at least in part, by the same gravitational dynamics that govern the Oort Cloud. The comet shower hypothesis adds a critical dimension to this picture. Under normal conditions, the influx of long-period comets into the inner solar system is a slow, steady trickle, a background drizzle of frozen objects dislodged by the galactic tide and by the accumulated perturbations of distant stellar encounters. This background rate is low enough that the probability of a significant cometary impact on Earth in any given million-year period is small. But during a comet shower triggered by a close stellar flyby, that rate spikes dramatically. The simulations are clear on this point. A sufficiently close and massive stellar passage can increase the flux of comets into the inner solar system by a factor of 10 or more, sustained over a period of 2 to 4 million years. During such a shower, the probability of a large impact rises correspondingly, and the chance of multiple large impacts within a geologically short period becomes non-trivial. If the Chicxulub impactor was indeed a comet rather than an asteroid, then the mass extinction it caused may have been the direct result of a stellar flyby that occurred tens of millions of years before the impact itself. The star would have been long gone by the time the comet arrived. The cause and the effect would have been separated by an abyss of time so vast that no observer could have connected them. The comet would have appeared to come from nowhere, a bolt from the black, unprovoked and unexplained. But it would not have come from nowhere. It would have come from the Oort Cloud, and it would have been sent there by gravity. There is another dimension to this problem that is often overlooked, and it concerns the galactic tide. The galactic tide is the differential gravitational force exerted on the solar system by the mass distribution of the Milky Way galaxy. Just as the Moon's gravity raises tides on Earth by pulling more strongly on the near side of the planet than on the far side, the galaxy's gravity pulls more strongly on objects closer to the galactic center than on objects farther away. For the Oort Cloud, this tidal force is significant. It acts slowly and steadily, continuously torquing the orbits of comets in the outer cloud, rotating their orbital planes, and gradually changing their perihelion distances, the closest points of their orbits to the Sun. Over millions of years, the galactic tide is the single most important mechanism for feeding comets from the Oort Cloud into the inner solar system. It is the background music, the steady hum, the baseline against which the punctuated percussion of stellar flybys is played. The interplay between the galactic tide and stellar encounters is complex and not yet fully understood. In some cases, the two forces reinforce each other. A stellar flyby nudges a comet's orbit into a configuration where the galactic tide can then slowly lower its perihelion over the next few million years, eventually delivering it to the inner solar system. In other cases, they work at cross purposes, with the galactic tide rotating an orbit away from the path that a stellar perturbation had set it on. The net result is a complicated, stochastic process in which the arrival of any individual comet is essentially unpredictable, but the statistical properties of the comet flux can be modelled and, to some degree, forecast. The flux varies over time, rising during comet showers and falling between them, modulated by the history of stellar encounters and the slow secular changes in the galactic tidal field as the solar system moves through different regions of the galaxy. This brings us to a concept that is central to understanding the problem, but that is difficult to convey in words, because it involves timescales that the human mind was never designed to grasp. The concept is the delay time, the interval between the perturbation that dislodges a comet from the Oort cloud and the moment that comet arrives in the inner solar system. For comets dislodged from the outer Oort cloud, this delay can be enormous, measured in millions or even tens of millions of years. The comet does not fall straight in. It follows an elongated elliptical orbit, crawling inward at first at speeds barely faster than walking pace, slowly accelerating as it drops deeper into the sun's gravity well, but taking eons to traverse the immense distance between the outer cloud and the planetary region. This means that the inner solar system at any given moment is being bombarded not by comets dislodged by the most recent stellar flyby, but by comets dislodged by flybys that occurred millions of years ago. The pipeline has a delay. The consequences lag behind their causes by intervals that can exceed the lifetimes of entire species. Let us trace the mechanics of how this process works, step by step, because the details matter and the chain of causation is longer and more intricate than it first appears. The Oort cloud is not a disk. Unlike the Kuiper belt, which lies roughly in the plane of the solar system, flattened by the gravitational influence of the planets, the Oort cloud is spherical. It surrounds the sun in every direction, above, below, and to all sides, forming a vast bubble of frozen material centered on our star. Its inner edge is believed to begin somewhere around 2,000 astronomical units from the sun, in a region sometimes called the Hills cloud or the inner Oort cloud, named after Jack Hills. Its outer edge extends to perhaps 100,000 astronomical units, roughly 1.6 light-years, where the sun's gravity finally loses its grip and objects drift free into interstellar space, becoming orphans, wanderers in the void between the stars. At the outermost reaches of this cloud, the comets orbit so slowly and so loosely that the gravitational influence of the sun is barely stronger than the combined gravitational influences of the rest of the galaxy. The galactic tide, the cumulative gravitational pull of all the matter in the Milky Way, exerts a steady force on these objects, slowly changing their orbital planes, slowly rotating their trajectories, occasionally nudging their closest approach to the sun, their perihelion distance, into the range where they enter the inner solar system and become visible as comets. These objects exist on a knife's edge between being bound to our star and drifting free into the galactic population of rogue bodies. They are citizens of a borderland, not quite part of the solar system and not quite free of it. Their allegiance to the sun is paper-thin, and any passing influence, however slight, can tear it. When Scholz's star passed through this region 70,000 years ago, it would have exerted a gravitational force on every object it came near. That force would have been small, measured against everyday scales. The red dwarf component of Scholz's star has a mass of only about 8.6% of the Sun's mass, roughly 86 Jupiter masses. The brown dwarf companion adds roughly another 6%, about 65 Jupiter masses. Together, the binary system masses about 14% of a solar mass, or roughly 151 Jupiter masses. That is not a lot of gravitational pull by stellar standards. But for objects already on the edge of gravitational freedom, even a small force can matter enormously. The analogy is a marble balanced on the rim of a bowl. The marble might sit there for millions of years, perfectly stable, perfectly balanced, undisturbed by anything in its environment. But flick it, even gently, and it begins to roll. It rolls inward, gaining speed, accelerating as it descends toward the center of the bowl. In the case of an Oort cloud comet, the center of the bowl is the sun, and the path inward takes that comet through a gauntlet of planetary orbits, including the orbit of Earth. A landmark 2018 study, published by researchers at the Max Planck Institute, calculated the effect of Scholz's star's passage on the Oort cloud with considerable precision, using N-body simulations, a computational technique that models the gravitational interaction between multiple bodies simultaneously. The researchers tracked the trajectories of tens of thousands of test particles representing Oort cloud objects as Scholz's star passed through the cloud. The results showed that the encounter perturbed a small but measurable number of comets. Objects in the outer Oort cloud, at distances of 50,000 to 100,000 astronomical units, experienced the greatest perturbation. Some had their orbits altered enough to send them on trajectories that would eventually bring them into the inner solar system. But the perturbation was not dramatic in the immediate sense. This was not a cosmic catastrophe on a human timescale, not a sudden rain of fire and ice. The combination of Scholz's star's low mass and high velocity, approximately 83 kilometers per second relative to the Sun, meant that the encounter was brief and the perturbations were modest. A more massive star, passing at the same distance but moving more slowly, would have caused far greater disruption. A sun-like star, lingering in the Oort cloud for hundreds of thousands of years, would have been an entirely different story, one with potentially devastating consequences. But here's the problem. The comets dislodged by Scholz's star 70,000 years ago are not going to arrive in the inner solar system tomorrow, or next year, or next century, or even next millennium. They are falling inward on orbits that take hundreds of thousands, or even millions of years to complete. Right now, at this moment, they are somewhere in the vast darkness between the Oort cloud and the orbit of Neptune, drifting sunward at speeds too slow to detect, on trajectories too uncertain to predict. We cannot see them. We do not know how many there are. We do not know when they will arrive or where they will pass. They are invisible, silent, and inexorable, falling sunward through the dark between the planets, carrying the frozen chemistry of the early solar system in their cores, trailing nothing, reflecting nothing, as cold and dark as the space around them. And the first sign of their arrival could be a point of light in the sky that grows brighter over the course of weeks and months, resolving into a fuzzy coma, developing a tail, a comet on an inbound trajectory that might pass harmlessly at a distance of millions of miles, or might not, and it gets worse. Scholz's star is only the most recent visitor we have positively identified. The record of stellar flybys extends across the full history of the solar system, and that record is almost certainly deeply incomplete. In 2015, the same year Mamajek published his findings about Scholz's star, other research teams used data from the European Space Agency's Hipparcos satellite, launched in 1989 and operated until 1993, to identify several other stars that have made or will make close approaches to the Sun. Gliese 710, a well-studied orange dwarf star of spectral type K7, currently located about 63 light-years away in the constellation Serpens Cauda, is predicted to pass within roughly 1.2 light-years of the Sun, in about 1.35 million years. Subsequent analyses using Gaia data have refined this estimate dramatically, suggesting the star may come as close as 0.2 light-years, or roughly 13,000 astronomical units, which would place it deep within the inner Oort cloud, far closer than Scholz's star ever penetrated. And Gliese 710 is considerably more massive, at roughly 60% of the Sun's mass, or about 6 times heavier than the entire Scholz's star binary system. The gravitational disruption it could cause would dwarf anything Scholz's star inflicted. It would be the difference between tossing a pebble into a pond and throwing a boulder. Then, in 2018, the European Space Agency released the second dataset from its Gaia spacecraft, a mission of staggering ambition and revolutionary capability. Gaia was designed to map the positions, distances, and three-dimensional motions of over 1 billion stars in the Milky Way with a precision that had never before been achieved. It measured stellar positions to an accuracy of a few tens of microarcseconds, roughly equivalent to detecting the diameter of a human hair from a distance of 1,000 kilometers. It measured stellar velocities to within fractions of a kilometer per second. With this extraordinary data set, astronomers could trace stellar trajectories forward and backward in time with a level of confidence that had simply never been available before. The results were sobering. Using Gaia data, a team led by Corinne Baylor-Jones at the Max Planck Institute for Astronomy identified dozens of stars that have passed, or will pass, within 2 parsecs of the Sun. 2 parsecs is roughly 6.5 light-years. Within that radius, stars are close enough to exert at least some gravitational influence on the outermost regions of the Oort cloud. The team found that, on average, approximately 20 stars pass within 2 parsecs of the Sun every million years. Some come much closer. The statistical analysis suggested that a star passes within 1 light-year of the Sun, roughly once every 100,000 years, and within half a light-year, roughly once every 900,000 years. Over the 4.6 billion year age of the solar system, those frequencies add up to staggering totals, roughly 46,000 close encounters within 1 light-year, roughly 5,000 encounters within half a light-year, which places them well inside the Oort Cloud. 5,000 stars passing through the Oort Cloud over the course of solar system history, each one a potential trigger for a comet shower, each one potentially sending a cascade of icy projectiles toward the inner solar system, each one leaving a gravitational imprint on the cloud structure that persists for millions of years after the star has receded into the distance. The Oort Cloud we see today, or rather the Oort Cloud we infer today, is the cumulative product of all these encounters, layered on top of each other like geological strata, each passage leaving its own subtle signature in the distribution and orbits of the cloud's inhabitants. The history of our solar system is not a story of stability and isolation. It is a story of repeated, invisible disruption, of ongoing vulnerability, of a boundary that is crossed again and again by objects we cannot predict. The Oort Cloud has been stirred, shaken, depleted, and perhaps partially replenished over billions of years by a parade of passing stars that we will never fully catalogue. Scholz's star is not an anomaly. It is a single data point, one point in a pattern that stretches across the entire lifetime of our cosmic home. And we are only now, in the last decade, beginning to see that pattern clearly. The implications extend well beyond comets. The gravitational influence of a passing star does not stop at the Oort Cloud. If a star comes close enough, and if it is massive enough, its gravity can perturb objects much deeper in the solar system. The Kuiper belt, for instance, is more tightly bound to the Sun than the Oort Cloud, but it is not invulnerable. A sufficiently close stellar passage, one within a few hundred astronomical units, could alter the orbits of Kuiper belt objects, potentially explaining some of the unusual orbital clustering that astronomers have observed among the most distant trans-Neptunian objects. Some researchers have even speculated that the hypothetical planet 9, a massive, undiscovered planet believed by some to orbit in the far outer solar system based on gravitational anomalies, first identified by astronomers Konstantin Batygin and Mike Brown at Caltech in 2016, could have a connection to past stellar encounters. Perhaps it was captured from a passing star system during a close flyby billions of years ago. Perhaps its orbit was shaped by the cumulative gravitational influence of many encounters over the solar system's history. These ideas remain speculative, but they illustrate the breadth and depth of influence that stellar passages can have, reaching far beyond the fragile outer shell of the Oort Cloud into the more familiar territories of the planetary system. There is also the deeper question of what happens to the planets themselves during a very close encounter, one closer than anything we have documented so far. The 8 known planets orbit the Sun at distances ranging from roughly 36 million miles for Mercury to about 2.8 billion miles for Neptune. These orbits are stable and deeply bound to the Sun's gravity. A passing star at 0.82 light-years, the distance of Scholz's star's closest approach, would have had no measurable effect on any of them. The gravitational tug would have been infinitesimally small compared to the Sun's grip. But what about a closer passage? What about a star that comes within 1,000 astronomical units? Within 500? Within 100? At those distances, the gravitational arithmetic changes dramatically. The tidal force of a passing Sun-like star at 100 astronomical units would be strong enough to noticeably perturb the orbit of Neptune, shifting its eccentricity and inclination by measurable amounts. These changes would be small in the immediate term, but orbital mechanics is a domain where small changes accumulate relentlessly. Over millions of years, slight perturbations compound, feeding back on each other through gravitational resonances, leading to cascading instabilities that can ripple inward through the entire planetary system. And numerical simulations conducted by multiple research groups including work by Jacques Lascar at the Paris Observatory, have shown that even without external perturbations, the inner solar system is chaotic on timescales of a few billion years. There is a small but non-zero probability that Mercury's orbit could become unstable, leading to a collision with Venus or ejection from the solar system entirely within the next 5 billion years. Add the gravitational nudges of passing stars into the calculation, and the timeline of instability may shorten. Consider for a moment the perspective of an observer living 70,000 years ago. A member of Homo sapiens, perhaps on the plains of Africa, perhaps in what is now Europe or Southeast Asia. That person would have looked up at the night sky and seen roughly the same stars we see tonight. The constellations would have been slightly different, shifted by the proper motions of the nearest stars, but the sky would have been recognizable. And somewhere in that sky, too faint to see with the naked eye, Scholz's star would have been glowing at an apparent magnitude of roughly 11.4, far below the threshold of unaided human vision, which tops out at about magnitude 6.5. Even at its closest approach, it would have been invisible without a telescope. It came, it passed, and it left, without any earthly witness, without a single conscious mind aware of its presence. But it did not leave without a trace. The comets it nudged, the ice fragments it dislodged, the subtle gravitational perturbations it inscribed into the orbits of Oort Cloud objects. These effects are still propagating through the solar system. They are still unfolding, still playing out across timescales that make human history look like a single frame in a very long film. We are living inside the slowly expanding consequences of a 70,000-year-old event, and we have no way of knowing what all of those consequences will ultimately bring. We can model them. We can estimate probabilities. We can run simulations. But we cannot know with certainty whether a comet dislodged by Scholz's star will one day cross our path. But here's what makes this truly terrifying. In the years since the discovery of Scholz's star, astronomers have pursued multiple lines of investigation to understand the broader phenomenon of stellar flybys and their consequences for our solar system. Each approach has revealed new details, new connections, and new uncertainties. Each one has peeled back another layer of the problem, only to expose a deeper and more troubling question beneath. What follows is a careful examination of 5 major avenues of inquiry, each offering a different lens through which to view the vulnerability of our cosmic home, and each one in its own way incomplete, each one revealing not just what we know, but how much we do not. The first avenue is the detailed study of Scholz's star itself, its mass, its velocity, the precise geometry of its passage, and the specifics of the perturbation it caused. After Mamajek's initial 2015 paper established the close approach, subsequent research teams devote considerable effort to refining the encounter parameters. These details are not academic trivia. They determine, with physical precision, how many comets were dislodged, how far inward they were sent, and over what time scale they will arrive in the inner solar system. The binary system of Scholz's star consists of 2 components. The primary is a red dwarf with a spectral classification of M9, placing it near the very bottom of the main sequence of hydrogen-burning stars. Its mass is estimated at roughly 86 thousandths of the Sun's mass, which is to say, not quite 1/10 of a solar mass, or roughly 90 Jupiter masses. Its luminosity is minuscule by stellar standards, perhaps 1/50th of 1% of the Sun's luminosity. If you replaced the Sun with Scholz's star's primary, Earth would receive so little energy that the oceans would freeze solid within decades, and the atmosphere itself would begin to condense and snow out onto the surface. The companion is a T-type brown dwarf, a substellar object with a mass of roughly 65 Jupiter masses, which translates to approximately 6% of the Sun's mass. Brown dwarfs are sometimes described as failed stars, objects that formed like stars from collapsing clouds of gas and dust, but never accumulated enough mass to ignite sustained hydrogen fusion in their cores. They glow dimly from the residual heat of their gravitational contraction, cooling slowly over billions of years, fading from infrared warmth to near invisibility. Together, the binary system has a combined mass of approximately 9.2% of the Sun's mass. In the world of stellar encounters, This is small. The gravitational perturbation a passing star inflicts on the Oort cloud scales directly with its mass, and inversely with its distance and its speed. A star 10 times heavier would cause 10 times more disruption at the same distance and velocity. Scholz's star, being so lightweight, was not an efficient perturber. It nudged the Oort cloud, but gently. It whispered where a larger star would have shouted. The encounter velocity is equally important to the outcome. Scholz's star was moving at approximately 83 kilometers per second relative to the Sun at the time of closest approach. To put that in human terms, that is roughly 186,000 miles per hour, or about 299,000 kilometers per hour. This is fast even by the standards of stellar motion in the solar neighborhood, where typical relative velocities are around 20 to 40 kilometers per second. At 83 kilometers per second, the star transited the outer Oort cloud in a matter of tens of thousands of years, a brief encounter by cosmic standards. The gravitational impulse, the total change in velocity imparted to each comet, depends not just on the force of gravity, but on the duration of the encounter. A faster passage means less time for the force to act, and therefore a smaller impulse. A slower star, lingering in the Oort cloud for hundreds of thousands of years, would have accumulated more perturbation on each object it encountered, dislodging more comets and sending more material cascading sunward. The high velocity of Scholz's star further reduced its impact on the cloud. The combination of low mass and high speed meant that Scholz's star was, in a certain quantifiable sense, the mildest possible type of intruder. It was a whisper in a library, not a shout in a canyon. And yet even this whisper left traces that we can detect. Research published in 2018 by Carlos de la Fuente Marcos and Raúl de la Fuente Marcos at the Complutense University of Madrid analyzed a sample of known hyperbolic objects, bodies whose orbital energy suggests they are not bound to the Sun and may have originated from the outer solar system or from beyond the solar system entirely. The researchers looked at the radiance of these objects, the points on the sky from which they appeared to originate, when their trajectories were traced backward. They found a statistical clustering of radiance in the direction of the constellation Gemini, which is roughly consistent with the direction from which Scholz's star approached our solar system. This is not definitive proof of a causal connection. The sample size was small, fewer than 24 objects, and other explanations are possible, including random statistical fluctuation. But it was the first observational hint, the first forensic clue, suggesting that Scholz's star's passage may have left a detectable fingerprint in the present-day population of objects entering our neighborhood. A calling card, faint but legible, left by a visitor 70,000 years gone. The limitation of this first avenue of inquiry is clear. We have only one confirmed close encounter to study in detail, and it was a gentle one. One data point does not make a pattern. It gives us a glimpse but not a panorama. To understand the broader phenomenon, to assess the true frequency and severity of stellar flybys across the history of the solar system, we need a census. And that brings us to the second avenue. The second avenue of investigation has been the use of the Gaia spacecraft to construct precisely that census, a comprehensive catalogue of stellar encounters, past and future, across the full sweep of galactic time accessible to our instruments. Gaia, launched by the European Space Agency in December of 2013 from the Guiana Space Center in French Guiana, is one of the most ambitious and precise astronomical instruments ever built. Positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth, it continuously scans the sky, measuring the positions, brightnesses, distances, and three-dimensional velocities of stars with a precision that was unimaginable a generation ago. The Gaia data releases have been transformative for the field of stellar encounter studies. The first release, in September of 2016, provided positions and brightnesses for over 1 billion stars. The second release, in April of 2018, added proper motions, parallaxes, and radial velocities for millions of them. The third release, in June of 2022, expanded the dataset further with spectroscopic measurements, orbital parameters for binary systems, and refined astrometric solutions for nearly 2 billion sources. With each release, the map of our stellar neighborhood has become sharper, more complete, and in many respects more concerning. Corinne Baylor-Jones, who has led much of the close encounter analysis using Gaia data, identified hundreds of stars with past or future close approaches to the Sun. The methodology is conceptually simple. Take the current position and velocity of each star, integrate its orbit forward and backward through the gravitational field of the galaxy, and note whenever it passes within a specified distance of the Sun. In practice, the work is enormously complex, requiring careful treatment of measurement uncertainties, galactic gravitational potential models, and the chaotic dynamics of stellar orbits over millions of years. Among the most notable results is the refined trajectory of Gliese 710. Using Gaia's precise measurements, Baylor-Jones and colleagues determined that this star will pass within approximately 10,300 astronomical units of the Sun in roughly 1.35 million years. That distance places it well within the Oort Cloud, significantly deeper than Scholz's star penetrated, and Gliese 710 is substantially more massive, roughly 60% of the Sun's mass, about 6 times heavier than the Scholz's star binary. It will also likely be moving more slowly than Scholz's star was, which means it will spend more time in the Oort Cloud, exerting its gravitational influence for a longer period. The combination of greater mass, close distance, and longer interaction time means the perturbation from Gliese 710 could be many times greater than anything Scholz's star caused. Simulations suggest it could send a genuine pulse of comets into the inner solar system, a shower that would unfold over the following 2 to 4 million years, elevating the impact rate on all the inner planets, including Earth. But Gliese 710 is only the most prominent example. Baylor-Jones identified many other candidates. Some are approaching now, their closest approach still centuries or millennia in the future. Some passed millions of years ago, their effects long since absorbed into the background dynamics of the Oort Cloud. Some have such uncertain trajectories that their projected closest approach distance spans a range from a few thousand astronomical units to several light years, making it impossible to assess their significance with any confidence. The uncertainties in the data, particularly in radial velocity measurements, propagate forward and backward in time, growing larger with each additional year of projection. A star whose radial velocity is uncertain by just 2 kilometers per second today could end up being off by hundreds of thousands of astronomical units in its projected position 1 million years from now. We know the general direction stars are moving in. We know approximately how fast. But approximately is not enough when we are trying to determine whether a particular star will thread the needle of the Oort Cloud or sail past at a safe distance. And here is the fundamental limitation of the Gaia approach, the gap that no amount of data processing can close. Gaia can only measure stars it can detect. The faintest objects, the small red dwarfs lurking at the bottom of the main sequence, the brown dwarfs glowing only in the infrared, the old white dwarfs that have cooled to near invisibility, the free-floating planets with no luminosity of their own. All of these frequently fall below Gaia's detection threshold, especially at larger distances or in crowded stellar fields near the galactic plane. Scholz's star itself, despite being only about 20 light-years away at the time of its discovery, was so faint that it had been missed by every previous sky survey, until Ralph Dieter Scholz specifically went looking for faint nearby stars. How many other similarly faint stars have passed close to the Sun without anyone noticing? How many are approaching now, invisible in our catalogues, unregistered in our databases? The answer is sobering. We do not know, and we have no reliable way to estimate how many we are missing. The third avenue of investigation is the study of the Oort Cloud itself, or rather, the deeply frustrating attempt to study it, because the Oort Cloud remains one of the most mysterious and poorly understood structures in the entire solar system. No direct observation of an Oort Cloud object in its native environment has ever been made. We have never imaged the cloud. We have never resolved an individual object within it. We have never sent a probe into it, and no probe currently in operation will reach it within the lifetime of anyone alive today. Voyager 1, the farthest human-made object from Earth, launched in 1977, is currently about 165 astronomical units from the Sun, moving outward at about 17 kilometers per second. At that rate, it will not reach the inner edge of the Oort cloud for roughly 300 years. It will not traverse the full extent of the cloud for another 30,000 years after that. And Voyager 1 carries no instruments capable of detecting the small, dark, frozen objects that populate the cloud even if it were surrounded by them. It would fly through the Oort cloud in complete ignorance of its inhabitants. Everything we know about the Oort cloud is therefore inferred from the orbits of long-period comets that fall into the inner solar system from its depths. Long-period comets are comets with orbital periods greater than 200 years. Many have periods measured in thousands, tens of thousands, or even millions of years. Their orbits are enormously elongated ellipses, stretching from the far reaches of the solar system to within a few astronomical units of the Sun, where they briefly become visible before swinging back out into the darkness. The distribution of these orbits, their orientations in space, their orbital energies, their arrival directions, provides our only window into the structure of the cloud from which they originated. In the 1950s, Jan Oort analysed the orbits of 19 long-period comets and noticed a peculiar clustering in their orbital energies. A disproportionate number had energies consistent with an origin at distances of roughly 20,000 to 100,000 astronomical units from the Sun. This clustering, now called the Oort spike, suggested that a vast reservoir of comets existed at those distances. Oort proposed that this reservoir was spherical, formed during the early history of the solar system when the giant planets, particularly Jupiter and Saturn, gravitationally ejected billions of planetesimals outward into distant orbits where they remained, frozen and inert, for billions of years. The hypothesis has been extensively developed since then, incorporating detailed models of how the Oort cloud formed, how it is maintained, and how comets are delivered from it into the inner solar system. The delivery mechanism involves two primary forces acting in combination. The first is the galactic tide, a steady gravitational force arising from the overall distribution of mass in the Milky Way galaxy. The galactic tide acts on the Oort cloud continuously, slowly torquing the orbital planes of its inhabitants, gradually reducing the perihelion distances of some comets until they enter the inner solar system. The second force is the perturbation from passing stars, which acts episodically and unpredictably, injecting bursts of comets on timescales determined by the frequency and severity of close encounters. Separating these two forces in the observational record is one of the great challenges of Oort cloud science, and it is a challenge that has not yet been fully met. The observed distribution of long-period comet orbits is the result of both forces acting simultaneously over 4.6 billion years. Their effects superimposed, intertwined, and frequently indistinguishable. Some researchers have attempted to identify the specific signatures of individual stellar encounters in the comet record, looking for excesses of comets arriving from particular directions that would correspond to the approach direction of a known or hypothesized passing star. The logic is sound, but the practical difficulties are formidable. The comets take millions of years to arrive. They are spread out over vast timescales, and the signal from any single encounter is faint against the continuous background produced by the galactic tide. The fourth avenue of investigation is the search for connections between stellar flybys, comet showers, and mass extinctions on Earth. This is the question that captures the public imagination, and also the one that has proven most resistant to definitive answer. It is the question that transforms Scholz's star from an astronomical curiosity into a potential thread in the story of life and death on our planet. In 1984, paleontologists David Raup and Jack Sepkoski at the University of Chicago published a paper claiming to find a periodic pattern in the fossil record of marine extinctions over the past 250 million years. They argued that extinction events seemed to recur at intervals of roughly 26 million years, with a statistical significance that they claimed was difficult to explain by chance alone. If this periodicity were real, it would demand a periodic cause, an astronomical clock of some kind that triggers comet showers at regular intervals, sending waves of impactors crashing into Earth on a schedule set by celestial mechanics. Several hypotheses were proposed to explain the claimed periodicity. The most dramatic was the Nemesis hypothesis, put forward independently by multiple groups in 1984. The idea was that the Sun has an unseen companion star, a dim red or brown dwarf, orbiting at a distance of roughly 1 to 2 light-years on a highly elliptical orbit. Every 26 million years, Nemesis would reach perihelion, its closest approach to the Sun, and pass through the densest part of the Oort Cloud, triggering a comet shower that would rain destruction on the inner solar system for the following million years. The elegance of the idea was magnetic. A single unseen companion could explain a centuries-long pattern of mass extinctions. It would be the most consequential unseen object in the solar system. But the search for Nemesis came up empty. Infrared sky surveys spanning decades, most comprehensively the Wide Field Infrared Survey Explorer mission, WISE, launched in December of 2009, scanned the entire sky at wavelengths of 3.4, 4.6, 12, and 22 micrometers, sensitive enough to detect even the faintest brown dwarf within several light-years of the Sun. WISE found thousands of new brown dwarfs throughout the galaxy, but identified no candidate for Nemesis within the required distance range. The conclusion was unavoidable. If Nemesis existed at the predicted distance with any reasonable mass, WISE would have found it. The hypothesis, while never formally and absolutely disproven, has been effectively abandoned by the mainstream astronomical community. The Sun does not appear to have a Death Star companion lurking in the dark. A related hypothesis linked the extinction periodicity to the Sun's vertical oscillation through the galactic plane. As the solar system orbits the galactic center at roughly 220 kilometers per second, it does not travel in a flat circle. It bobs up and down through the disk of the galaxy like a horse on a carousel, crossing the dense galactic midplane roughly every 30 to 35 million years. During each crossing, the solar system encounters higher densities of stars, interstellar gas, and giant molecular clouds, all of which could perturb the Oort cloud more aggressively than the relatively empty space above and below the plane. This hypothesis remains under discussion, though the oscillation period does not precisely match the claimed extinction period, which introduces a tension that has never been fully resolved. Moreover, the statistical significance of the extinction periodicity itself has been repeatedly challenged. Some statistical analyses confirm it, others do not. The debate continues, decades after Alpern and Sepkoski's original paper. In 2015, theoretical physicists Lisa Randall and Matthew Rees at Harvard University proposed an inventive variation on the galactic oscillation idea. They suggested that a thin disk of dark matter concentrated in the galactic midplane could enhance the gravitational perturbation experienced by the Oort cloud during each plane crossing, focusing the comet shower into a narrower time window and making the extinction periodicity sharper than it would be from stellar encounters alone. The dark disk would be composed of a particular type of dark matter that can lose energy through radiation and collapse into a thin, dense structure, unlike the conventional cold dark matter that forms diffuse, spherical halos around galaxies. The idea was creative, even elegant, and it was testable in principle through precision measurements of stellar kinematics near the galactic plane, but it required a species of dark matter that has not been confirmed by any particle physics experiment or astrophysical observation. It remains a hypothesis resting on a hypothesis, intriguing but unproven. The numbers are striking when you survey the full scope of the problem. The Earth has experienced at least 5 major mass extinctions in the past 540 million years. The Ordovician-Silurian extinction, roughly 445 million years ago, the late Devonian extinction, roughly 375 million years ago, the Permian-Triassic extinction, roughly 252 million years ago, the Triassic-Jurassic extinction, roughly 201 million years ago, and the Cretaceous-Paleogene extinction, roughly 66 million years ago. In addition, there have been dozens of smaller extinction pulses and biodiversity crises. Some of these correlate with known impact events. Some correlate with volcanic eruptions. Some correlate with climate shifts. Many have no clear single cause. The web of causation is dense, tangled, and poorly constrained by the available evidence. Are any of these extinctions linked to stellar flybys and comet showers? The honest answer is, possibly, but we cannot yet say for certain. The physical chain of causation is plausible. Stellar flybys perturb the Oort Cloud. Perturbations send comets inward. Comets can hit planets. Impacts can cause extinctions. Every link in this chain is supported by established physics. But demonstrating that the chain actually connected in any specific historical case requires a level of evidence we do not yet possess. We cannot identify which specific star caused which specific comet to arrive on which specific trajectory at which specific time to cause which specific extinction. The causal chain is too long, too diffuse, and too poorly recorded in the geological and astronomical data. And yet there are tantalizing hints. The late Eocene epoch, roughly 34 to 36 million years ago, appears to have been a period of elevated bombardment. The Popigai crater in Siberia, 100 kilometers in diameter, and the Chesapeake Bay crater on the eastern seaboard of the United States, 85 kilometers across, both date to within a few 100,000 years of each other, suggesting a possible clustering of impacts that would be consistent with a comet shower. The Eocene-Oligocene boundary, which falls in this same general time window, saw a significant drop in global temperatures and a major turnover in both marine and terrestrial species. Is this a coincidence, or is it the echo of a star that passed through the Oort Cloud 40 or 50 million years ago, sending a wave of comets inward that arrived, spread over millions of years, and left their marks in craters and in the fossil record? We do not know. The evidence is suggestive but not conclusive, and the gaps in the record are wide enough to accommodate multiple interpretations. There is an additional complication that makes the search for comet shower signatures in the geological record even more challenging. Comets are fragile objects. Unlike rocky asteroids, which are held together by material strength and can survive the stress of atmospheric entry as large, coherent bodies, comets are loosely consolidated aggregates of ice, dust, and organic compounds often described as dirty snowballs, or more accurately, icy dirt balls. When they enter the inner solar system and are heated by the sun, they lose mass rapidly through sublimation, shedding gas and dust in the spectacular tails that make them visible. By the time a comet reaches the inner solar system, after a journey of millions of years from the Oort Cloud, it may have already undergone significant changes in its structure and composition. And if it strikes a planet, the impact signatures it leaves may be subtly different from those left by an asteroidal impactor, making it difficult to distinguish comet impacts from asteroid impacts in the crater record. The chemical fingerprints differ, the velocity distributions differ, the impact angles and energy profiles differ. And after millions of years of geological processing, erosion, burial, tectonic deformation and metamorphism, even these subtle distinctions can be erased or obscured beyond recognition. The search for a definitive link between stellar flybys and mass extinctions is therefore a problem that sits at the intersection of several disciplines, each with its own limitations. Astronomy, which can track stellar motions but only for the relatively recent past and near future. Paleontology, which records extinction events but with limited temporal resolution and incomplete spatial coverage. Geology, which preserves impact craters but loses them over time to erosion and plate tectonics. And computational physics, which can simulate Oort cloud dynamics, but must work with uncertain initial conditions and incomplete knowledge of the cloud structure. No single discipline can solve the problem alone. Progress will require the integration of all four, and it will require patience. The answers, if they come, will come slowly. The fifth avenue of investigation concerns the future. Scholz's star is receding, now roughly 22 light-years away, but other stars are approaching. The galactic dance continues, and our next partner is already crossing the floor. Gliese 710 will arrive in approximately 1.35 million years and pass deep into the Oort cloud. It is an orange dwarf star, smaller and cooler than the Sun, but far more substantial than Scholz's star, with a mass of approximately 60% of the Sun's mass and a luminosity of roughly 4%. It is currently unremarkable, an ordinary star in an ordinary part of the sky, visible to the naked eye only on the clearest, darkest nights. But its trajectory is extraordinary. Early estimates, based on Hipparco's data, placed its closest approach at roughly 1 light-year from the Sun, comparable to Scholz's star's passage. The Gaia mission changed everything. The refined trajectory, published using Gaia's second data release, suggested that Gliese 710 would pass within approximately 10,300 astronomical units, or about 0.16 light-years. That is 5 times closer than Scholz's star came. And at 6 times the mass, Gliese 710 would exert a gravitational influence on the Oort Cloud roughly 30 times stronger than Scholz's star did, assuming similar encounter velocities. The comparison is not hypothetical, it is arithmetic, and the arithmetic is alarming, but Gliese 710 is not alone. Other candidates have been identified in the Gaia data, including several faint low-mass stars whose approach trajectories are poorly constrained by current measurements. For each of these stars, the critical questions are the same. How close will it come? How massive is it? How fast will it be moving? And what will it do to the frozen bodies in the Oort Cloud? But the deeper and more unsettling problem is not the stars we can see approaching. It is the ones we cannot see. Brown dwarfs, old white dwarfs that have cooled to near invisibility, and free-floating planets, bodies ejected from their parent star systems by gravitational interactions during planetary formation. All of these populate the galaxy in vast numbers. Estimates suggest there may be as many free-floating planets as there are stars in the Milky Way, perhaps 100 to 400 billion of them, wandering through interstellar space without any stellar host, dark and cold and undetectable except at the closest ranges. A Jupiter-mass object, completely dark, approaching from any direction, could enter the outer Oort cloud before any current observatory could detect it. We would not see it coming. There is a particular scenario that astronomers have modelled with results that should give anyone pause. Imagine a star with roughly 1 solar mass, comparable in size and weight to our own Sun, passing through the Oort cloud at a distance of 10,000 astronomical units, moving at a relatively slow 20 kilometers per second. This is not an outlandish scenario. Stars of solar mass are common. Velocities of 20 kilometers per second are common, and distances of 10,000 astronomical units, while close, are well within the range of known and projected encounters. Simulations of this scenario suggest that such an encounter could dislodge hundreds of millions of comets from their stable orbits, sending them cascading into the inner solar system over the following 2 to 4 million years. The rate of comet bombardment would increase by a factor of 10 or more above the normal background rate, sustained across a period longer than the entire existence of the genus Homo. During that window, the probability of a significant cometary impact on Earth would increase correspondingly from negligible to merely very small but geologically significant. Under normal conditions, the background rate of significant cometary impacts on Earth is estimated at very roughly 1 every few hundred million years. During a comet shower triggered by a close stellar passage, that rate could rise to 1 every few tens of millions of years. On a human timescale, this remains a remote risk, far less likely in any given year than an earthquake or a volcanic eruption. But on a geological timescale, the timescale on which evolution operates, it is a near certainty. And it means that the impact history of Earth is not entirely a story of random, isolated events. It is partly a story written by the orbits of wandering stars, influenced by the gravitational choreography of the galaxy, shaped by forces that operate on scales far larger than our planet and far longer than our history. Something is wrong with our assumptions about the permanence of our cosmic environment. We have treated the solar system as if it were a sealed terrarium, a self-contained ecosystem with fixed boundaries and stable contents. Scholz's star has shown us that this picture is an illusion, a comfortable but incorrect simplification born of our inability to perceive the slowness of cosmic change. We live in an open system, connected to the galaxy by invisible gravitational threads that stretch across light years, and the galaxy is full of wandering stars. Each one is a potential intruder. Each one carries with it the possibility, however small, of altering the trajectory of comets that could, in turn, alter the trajectory of life on our planet. We cannot close the door. We cannot build a wall. We can only watch and try to understand what we are seeing. The deeper truth is not about Scholz's star. It is not about any single star or any single flyby or any single comet that may or may not be falling toward us right now. The deeper truth is about the nature of stability itself, and the dangerous comfort we take in assuming that the cosmos is orderly, that it follows rules we have already discovered, and that those rules guarantee our safety. We have grown up, as a civilization, with a model of the solar system that looks like a clockwork mechanism. The planets trace their ellipses, the comets follow their schedules, the asteroids remain in their belt. Everything has its place, and everything returns to its place, year after year, century after century, millennium after millennium. This model is useful, it is beautiful. It has allowed us to send spacecraft to every planet in the solar system and to predict eclipses centuries in advance. It is not wrong, exactly, but it is incomplete in a way that matters profoundly, in a way that could, under the right circumstances, matter existentially. The clockwork model works well on short timescales measured in human generations or even human civilizations. On those timescales, the solar system does behave predictably. The planets will be where we expect them to be. The seasons will cycle, the tides will rise and fall. We can launch a spacecraft today and know, with extraordinary precision, where Mars will be 3 years from now. This predictability has led us to believe that the solar system is fundamentally stable, that the arrangement we see today has always existed and will always exist, that the solar system is a finished product, polished and permanent. But the clockwork model breaks down on longer timescales. On timescales of millions and billions of years, the solar system is not a clock. It is more like a weather system. Small perturbations accumulate. Tiny gravitational nudges compound over eons. Chaotic dynamics amplify uncertainties until the future becomes fundamentally unpredictable. Not because our instruments are imprecise, but because the system itself is sensitive to conditions we can never fully specify. Jacques Lascar, one of the pioneers of this field, demonstrated in the early 1990s that the orbits of the inner planets, including Earth, are chaotic on timescales of roughly 5 million years. This means that beyond 5 million years into the future, we cannot predict with certainty whether Mars will remain in its current orbit or undergo a dramatic change. We cannot guarantee that a resonance between Mercury and Jupiter will not destabilize the inner solar system entirely. The clockwork is ticking, but it contains hidden springs, and some of those springs are wound to go off on timescales far longer than any human institution has existed to observe. And at the center of this long-term unpredictability sits the Oort Cloud, a vast reservoir of potential impactors, held in place by the thinnest possible gravitational margin, surrounded by a galaxy full of objects capable of tipping that margin. Let that sink in. The outer boundary of our solar system is not a wall, it is not a barrier, it is not a shield. It is a line drawn in water, constantly shifting, constantly being redrawn by forces we cannot control and can barely detect. Every star that passes through our neighborhood is a hand reaching into the water, disturbing the surface, sending ripples inward. Some of those ripples dissipate harmlessly, fading into the background noise of orbital dynamics. Some of them, given enough time and enough reinforcement, become waves. And those waves carry comets. Scholz's star was a small hand making a gentle disturbance, a whisper in the dark. But it is the disturbance itself that matters, not its magnitude. Because the disturbance proves that the system is open. It proves that the boundary is permeable. And it proves that the comets in the Oort Cloud, those ancient frozen relics from the dawn of the solar system, are not safely stored in some inviolable cosmic vault. They are loosely held, balanced on a razor's edge of gravitational loyalty, and they can be released by any passing influence strong enough to tip that balance. Consider the numbers once more. The Oort Cloud is estimated to contain somewhere between several hundred billion and perhaps 2 trillion objects, larger than 1 kilometer in diameter. The total mass of the cloud is uncertain, but may lie somewhere between 1 and 40 Earth masses, scattered across a volume of space so enormous that the average distance between neighboring objects is measured in millions of kilometers. These objects orbit at distances so vast that the Sun appears as merely the brightest star in their sky. At 50,000 astronomical units, the Sun would be a star of roughly negative first magnitude. Brilliant but clearly stellar, clearly just another point of light among thousands. At 100,000 astronomical units, the Sun would fade to roughly third magnitude, barely visible among the background stars of the Milky Way. An object at that distance orbits the Sun at a speed of roughly 100 meters per second, slower than a car on a highway, slower than a bicycle rider on a flat road. It takes millions of years to complete a single orbit. Time moves differently out there. Everything is slow. Everything is quiet. Everything is cold, hovering just a few degrees above absolute zero, around negative 270 degrees Celsius, in an environment so sparse and so dark that it is difficult to distinguish from interstellar space itself. This is not science fiction. This is the actual physical environment at the outer edge of our solar system, a freezing, near motionless desert of ice and rock, stretching in every direction for trillions of miles, inhabited by objects that have not been significantly heated by sunlight since the solar system was young. Some of these objects have been orbiting undisturbed for 4 billion years. Some of them predate the existence of complex life on Earth. They are time capsules, frozen witnesses to an era when the solar system was still taking shape, when the giant planets were still migrating through the disk of gas and dust that surrounded the young Sun, when the chemistry that would eventually lead to life was still being assembled in warm tidal pools on a young volcanic planet. And then a star wanders through. A small, dim star, moving fast, pulling on these ancient objects with its gravity as it passes. Most of the objects barely respond. Their orbits shift by fractions of a degree, by centimeters per second. The change is almost unmeasurable, but for some objects, those at the very edge, those already on orbits that take them to the threshold between bound and unbound, the nudge is enough. Their orbits elongate. Their closest approach to the Sun drops from tens of thousands of astronomical units to thousands, to hundreds, to tens. They begin to fall inward, slowly at first, drifting sunward under the Sun's faint but relentless pull, gaining speed as they descend deeper into the gravity well. The journey takes a very long time, hundreds of thousands of years, sometimes millions, but they are patient, they have nothing but time, and they are coming. This is the pipeline. The Oort Cloud is the reservoir. Stellar flybys are the trigger mechanism. The galactic tide is the background hum. And the inner solar system, where Earth orbits, where we build our cities and write our histories and raise our children, is the target zone, the terminus of the pipeline, the place where the comets arrive after their long silent journey from the outer dark. The pipeline has been flowing for 4.6 billion years. It has delivered comets to the inner solar system throughout the entire history of the Earth. Some of those comets brought water, some of them brought organic molecules, the chemical precursors of life itself. Some of them brought destruction, and some of them, the ones that have not yet arrived, are still in transit. Let that sink in. There are comets falling toward us right now. Comets dislodged from the Oort Cloud by stellar encounters that occurred thousands, tens of thousands, hundreds of thousands of years ago. Comets whose orbits were nudged by stars whose light has already passed us and faded into the distance. Comets that are invisible to our telescopes because they are still far too distant, still cold, still dark, still unilluminated by any source of light strong enough to reveal them. We do not know how many there are. We do not know when they will arrive. We do not know where they are going. They exist in a kind of statistical haze, a probability cloud of their own, defined not by certainty but by likelihood, by the mathematics of orbital mechanics and gravitational perturbation theory. They are real, they are physical, and they are beyond our ability to track. There is a paradox embedded in this realization, and it is worth stating plainly. The same physics that allows us to predict planetary positions with such exquisite precision also guarantees that we cannot predict the arrival of long-period comets with anything approaching the same accuracy. Planetary orbits are short, well observed, and dominated by a single gravitational influence, the Sun. Comet orbits from the Oort Cloud are immensely long, never observed in their entirety, and influenced by a chaotic tapestry of forces: the Sun, the planets, passing stars, the galactic tide, and molecular clouds, all acting on different timescales and in different directions. The planets are deterministic on human timescales. The comets are fundamentally stochastic. We live in a solar system where the near is predictable and the far is not, where the ground beneath our feet is solid, but the sky above our heads is ruled by probability. This paradox is not merely an intellectual curiosity. It has practical implications that extend far into the future of our species. We have built our entire understanding of celestial mechanics on the spectacular success of prediction. We predicted the return of Halley's comet in 1758, confirming Newton's gravitational theory and establishing the power of mathematical astronomy. We predicted the existence of Neptune in 1846, discovering a new planet through calculation before any telescope confirmed it. We predicted the exact moment of solar eclipses decades in advance and navigated spacecraft to pinpoint landings on distant worlds with errors measured in meters. These triumphs have given us enormous confidence in our ability to understand and control our relationship with the cosmos. But that confidence is calibrated to the short period, inner solar system domain where prediction works. It does not extend to the Oort Cloud. It does not cover the domain of long-period comets, and it is from that unpredictable domain that the greatest cosmic threats to life on Earth originate. Consider the difference in concrete terms. We currently track roughly 35,000 near-Earth objects, asteroids and short-period comets that orbit in the inner solar system and come close to Earth's orbit. We know their positions and velocities with high precision. We can project their trajectories decades or centuries into the future and identify any that might pose an impact risk. This is an extraordinary achievement, the product of decades of systematic surveying by programs like the Catalina Sky Survey, Pan-STARRS, and the upcoming Vera C. Rubin Observatory. We are building, for the first time in human history, a comprehensive map of the objects that could threaten us from within the inner solar system. But the Oort Cloud is a different world entirely. We cannot survey it, we cannot catalogue its contents, we cannot track the objects within it, and the comets it sends toward us arrive without notice, from any direction, on orbits we have never seen before. A long-period comet inbound from the Oort Cloud might not be detected until it is inside the orbit of Jupiter, perhaps 2 to 3 years before it reaches perihelion, if it happens to be on a collision course with Earth. That gives us, at best, a few years to respond. And for a comet 10 or 20 kilometers across, traveling at 50 kilometers per second, a few years might not be enough. The DART mission demonstrated that we can deflect a small asteroid if we hit it hard enough and early enough. But DART targeted an object roughly 160 meters across, traveling at a well-known velocity on a well-known orbit. A Chiron-sized or Hale-Bopp-sized object arriving from the outer solar system at twice the speed, discovered 2 years before impact, would be an entirely different engineering problem. We do not currently possess the technology to deflect such an object in such a time frame. We are, in a very real sense, defenseless against the Oort Cloud's largest projectiles. This vulnerability is not a failure of will or of investment. It is a structural feature of our cosmic environment. The Oort Cloud is too far away, too vast, and too dark to monitor. Its contents are too small and too cold to detect at any useful distance. And the comets it sends inward move too slowly for most of their journey to be distinguished from the empty space around them. By the time they become visible, they are already deep inside the solar system, committed to their inbound trajectory, moving too fast to stop. The detection problem and the deflection problem converge in the worst possible way. The objects we most need to see early are the ones we are least capable of detecting early, and the ones that arrive fastest are the ones we have the least time to divert. There is a further subtlety worth dwelling on. Not all stellar flybys are equal, and the differences between them are not merely quantitative, they are qualitative. A fast flyby, like Scholz's star's passage at 83 kilometers per second, is a brief impulse, a sharp nudge applied to the Oort Cloud's outer layers and then removed. The perturbation is concentrated in time and limited in scope. A slow flyby, like what Gliese 710 may deliver at a lower relative velocity, is qualitatively different. A slow-moving star lingers in the Oort cloud for longer, allowing its gravitational influence to accumulate over a longer period. The perturbation is distributed over more time and reaches deeper into the cloud. The comets affected are not just those at the very edge, but potentially those in the inner Oort cloud as well, objects at distances of 2,000 to 20,000 astronomical units that are more tightly bound and ordinarily more resistant to perturbation. A slow, massive intruder can reach down into layers of the cloud that a fast, lightweight visitor like Scholz's star could never touch. And the comets from those deeper layers, being on shorter orbits to begin with, would arrive in the inner solar system sooner, compressing the delay between perturbation and consequence. The water in your body, some fraction of it, may have arrived on a comet that was dislodged from the Oort cloud by a passing star billions of years ago. The oxygen you breathe, the carbon in your bones, the iron in your blood, all of these were forged in the hearts of ancient stars and distributed through the galaxy by processes that include, at one remove or another, the gravitational interactions that shape the Oort cloud, the mass extinction that cleared the way for the rise of mammals, and eventually for the evolution of primates, and eventually for the emergence of human beings, may have been triggered by an impactor that was set in motion by a stellar flyby hundreds of millions of years before it struck. The chain of causation stretches backward through time, link by link, from us to the comets to the Oort cloud to the wandering stars, and each link is made of gravity, the most patient and the most persistent force in the universe. We are, in ways we are only beginning to understand, the products of stellar encounters. Our existence is contingent on events that occurred at the outermost edges of the solar system, in the coldest and darkest regions of our sun's domain, set in motion by stars whose names we will never know. This is not a metaphor. This is not a poetic exaggeration. This is a straightforward consequence of the physics that governs the behavior of comets, stars, and planets over timescales of billions of years. We are connected to the galaxy not just by the light of distant stars, but by the gravity that binds us to a cloud of frozen objects that can, under the right conditions, fall from the sky and change everything. There is a thought experiment that captures the strangeness of our situation. Imagine you are standing in a vast field. It is a calm day. The sky is clear. The air is still. You feel perfectly safe. But beneath the field, buried deep in the soil, there is a network of underground rivers. You cannot see them. You cannot hear them. You do not know they are there. These rivers have been flowing for millions of years, slowly eroding the rock beneath your feet, creating caverns and tunnels and void spaces that weaken the ground you stand on. The ground looks solid. It feels solid. You can walk on it, build on it, plant on it, but it is not solid. It is honeycombed with invisible channels, undermined by processes you cannot detect, and one day, without warning, a sinkhole opens. The ground gives way, you fall, and you realize, too late, that the stability you took for granted was never as complete as you believed. The Oort cloud is the underground river, the stellar flybys are the erosion, and the ground we stand on, the apparent stability of our inner solar system, the regularity of our orbits, the predictability of our seasons, is thinner than we thought. We have been standing here for billions of years without falling, and we may stand here for billions more. The probability of a catastrophic impact in any given century is extremely small, but the ground is not solid, it never was, and the rivers are still flowing. There is one more dimension to this truth, one that scientists are only now beginning to explore with the quantitative rigor it deserves. It concerns the cumulative effect of many small perturbations rather than the dramatic effect of a single large one. We have been discussing stellar flybys as individual events, each with its own distance and velocity and gravitational influence. But the Oort cloud does not experience them as individual events. It experiences them as a continuous, never-ending rain of gravitational nudges, arriving from every direction, at every angle, with every conceivable combination of mass and speed. Some nudges cancel each other out, some reinforce each other, and over billions of years, the net effect is a slow, irreversible erosion of the cloud's outer layers, a gradual stripping away of the most weakly bound objects, a steady feeding of the inner solar system with comets that would otherwise have remained in cold storage forever. This is not a catastrophe. It is a process as natural and as inevitable as erosion on a riverbank, as predictable in its broad outlines as it is unpredictable in its specific details. The Oort Cloud is shrinking. It has been shrinking since the day it formed, and every comet that has ever graced the skies of Earth, every brilliant tale that has inspired myth and prophecy and scientific inquiry, is evidence of that shrinkage, a fragment of the cloud's outer edge that has been shaved off by the ceaseless action of the galaxy's gravitational weather. We live, then, not in a static system, but in a system that is slowly, continuously, irreversibly changing, shaped by forces that originate far beyond its borders and operate on timescales that make human history look like the blinking of an eye. The stability we perceive is real, but it is local, temporary, and conditional. It is the stability of a sandcastle between tides, beautiful and intricate, and destined to be reshaped by forces that have been in motion since long before it was built. What does all of this mean for us? For humanity, a species that has existed for perhaps 300,000 years, a species that has had organized civilization for roughly 10,000 years, a species that has had the ability to look beyond its own atmosphere for barely 4 centuries. It means, first and most fundamentally, that we are more connected to the cosmos than we typically appreciate. The popular image of space is one of emptiness, a vast dark void in which the Earth floats in splendid isolation, untouched and untouchable by the distant stars. This image is comforting. It is also wrong. We are not isolated. We are embedded. We are woven into a network of gravitational interactions that spans the entire galaxy, and events at the far edges of that network can propagate inward, slowly but inexorably, until they reach our doorstep. Scholz's star did not come close enough to threaten us directly. Its gravity was far too weak, its passage too brief, to perturb any object in the inner solar system by a measurable amount. But it touched the Oort Cloud, and the Oort Cloud touches us. It means, second, that the long-term future of life on Earth is subject to uncertainties that we cannot eliminate through any purely terrestrial effort. We can mitigate climate change. We can prevent nuclear war. We can prepare for pandemics. These are threats within our control, arising from forces within our atmosphere and our societies. But we cannot prevent a star from passing through the Oort Cloud. We cannot stop the gravitational perturbations that such a passage would cause. We cannot redirect millions of comets that are already falling inward on trajectories established millions of years ago by gravitational interactions we never witnessed. The best we can do, and this is neither trivial nor hopeless, is to detect them, track them, and, if our technology permits, deflect any that pose a direct threat. Programs like NASA's Planetary Defense Coordination Office and the European Space Agency's Near-Earth Object Coordination Center are steps in this direction. The DART mission, which successfully demonstrated the ability to alter the trajectory of a small asteroid by crashing a spacecraft into it in 2022, was a proof of concept for exactly this kind of intervention. But we are still far from having the capability to monitor the full scope of the threat. The objects in the Oort Cloud are too small, too distant, and too numerous for any existing or planned observatory to catalogue. Long-period comets that originate from the Oort Cloud can arrive from any direction, and many of them are discovered only months or even weeks before they reach perihelion, their closest approach to the Sun. A comet on a direct collision course with Earth, arriving from the outer solar system for the first time, would be cold and dark until it entered the inner solar system and began to sublimate, developing the characteristic coma and tail that make comets visible. By the time we spotted it, we might have only a few years of warning, perhaps less. This is why the Vera C. Rubin Observatory, currently preparing for its decade-long legacy survey of space and time, represents such a significant advance. By surveying the entire visible sky every few nights, it will dramatically increase our detection rate for faint, distant objects, including long-period comets on their first approach to the inner solar system. It will not solve the problem entirely, as no single instrument can, but it will narrow the window of ignorance. It will give us more time to see what is coming, more time to assess the risk, more time to respond, And time, when you are dealing with objects moving at tens of kilometers per second on collision trajectories, is the most precious resource of all. There is a particular kind of humility that comes from contemplating these facts. It is not the humility of insignificance, although that too is appropriate. It is the humility of contingency, the recognition that our existence is not guaranteed by any law of physics, not protected by any cosmic principle, not ensured by any fundamental feature of the universe. We exist because, so far, no large comet has struck Earth during the span of our civilization. We exist because the most recent stellar flyby happened to be mild, caused by a star too small and too fast to do serious damage. We exist because the geometry of stellar encounters over the past 10,000 years happened to be benign, the cosmic dice rolling in our favor, time after time after time. We exist because we have been lucky, and luck, by definition, does not guarantee the future. This is not a reason for despair. Despair is not a useful response to astronomical risk, any more than it is a useful response to the inevitability of death. It is, instead, a reason for awareness, a reason to understand our cosmic environment as clearly and completely as we can, so that we are not caught off guard by dangers we could have anticipated. The discovery of Scholz's star is, in this sense, a gift. It has given us a concrete, well-characterized example of a process that we understood theoretically, but had never observed directly. It has turned an abstract possibility into a documented event, and it has catalyzed a new generation of research into the dynamics of the Oort Cloud, the frequency of stellar encounters, and the long-term impact history of the Earth. It has also, quietly, changed the way astronomers think about the solar neighborhood. Before the discovery of Scholz's star, the study of stellar flybys was largely theoretical, a subfield of celestial mechanics pursued by a relatively small number of specialists. The encounter rates were estimated from statistical models. The perturbation effects were calculated from simulations, but there was no confirmed example, no specific star that could be pointed to as evidence that the process had actually occurred in our solar system's recent past. Scholz's star changed that. It provided a case study, a concrete instance that could be analyzed, refined, and used as a benchmark against which to test theoretical predictions. It was the difference between knowing that earthquakes can happen and standing in a building during one. The abstract became personal, and the urgency of the research increased accordingly. In the years since the discovery, several groups have launched systematic efforts to identify other close encounters, both past and future. The Gaia mission has been the primary engine of this work, but it is not the only one. Ground-based radial velocity surveys continue to refine the trajectories of nearby stars. Infrared surveys like the upcoming Nancy Grace Roman Space Telescope, set to launch later this decade, will have the sensitivity to detect faint brown dwarfs and very low-mass stars that Gaia and WISE may have missed, potentially revealing additional close encounters that remain hidden in the current data. Each new discovery adds another data point to the emerging picture of our galactic environment, a picture that is slowly, painstakingly resolving from a vague statistical blur into a detailed portrait of the traffic patterns around our star. There is something poignant about the timing. 70,000 years ago, when Scholz's star slipped through our Oort Cloud, humanity was in its infancy. We were anatomically modern, but culturally nascent, just beginning the long journey from stone tools to spacecraft, from campfire stories to quantum mechanics. We had no concept of a solar system, no knowledge of comets or orbits or gravitational attraction. We did not know that we lived on a sphere, or that the sphere orbited a star, or that the star was one of hundreds of billions in a galaxy, that itself was one of hundreds of billions of galaxies in an observable universe 93 billion light-years across. We were blind to the cosmos in every meaningful way. And now, 70,000 years later, we have not only discovered the existence of Scholz's star, but we have traced its path backward through time and determined, with high statistical confidence, that it passed through our Oort Cloud during the era of our ancestors. We have looked into the past and recovered an event that no one at the time could have perceived, an event that left no mark on any human memory, no trace in any oral tradition, no record in any cave painting. We reconstructed it from the faintest of signals, a dim star with an unusual motion, a set of radial velocity measurements, a convergence of orbital mechanics and astrometric data. We assembled a story that spans the full breadth of the solar system and the full depth of human evolution, and we did it from a planet orbiting an ordinary star in an unremarkable corner of an average galaxy. That is an achievement worth pausing over. It speaks to something fundamental about what our species is capable of. We are small, we are fragile. We live on a thin skin of rock and water, orbiting an ordinary star in the outer arm of a spiral galaxy. Our individual lives are measured in decades, our civilizations in millennia, but we can see backward in time. We can trace the paths of stars. We can model the behavior of comets at the outermost edges of the sun's gravitational domain. We can peer into regions of space we have never visited and reconstruct events that occurred when our ancestors were painting red ochre on cave walls by firelight. There is a word for what we are doing when we reconstruct events like the flyby of Scholz's star. That word is not science, although science is the method. The word is remembering. We are remembering events that no human being witnessed, events that left no conscious impression on any living mind. We are building a memory that extends beyond the biological limits of our species, a memory that reaches back 70,000 years and more, a memory encoded not in neurons but in mathematics, not in stories but in equations, not in tradition but in data. We are creating what might be called a cosmic memory, a record of events that the universe itself does not remember, but that we, through the extraordinary machinery of telescopes and computers and human ingenuity, have chosen to preserve. This is, in some sense, the deepest implication of the Scholz's star discovery. It is not just that a star passed close to us. It is that we found out. It is that we noticed. It is that we cared enough to look, and skilled enough to reconstruct, and humble enough to be astonished by what we found. The universe is under no obligation to be comprehensible, and yet it yields to inquiry. The cosmos does not owe us its secrets, and yet we have pried some of them loose. With instruments made of glass and silicon, and with minds evolved for tracking prey across African savannas, minds that have somehow, improbably, learned to track the paths of stars across the galaxy. We are, in this one narrow but extraordinary sense, larger than the cosmos that contains us. We are the universe becoming aware of its own machinery, and that awareness, fragile and imperfect as it is our greatest tool and our only defense. We began tonight with a quiet visitor, a small, dim binary star that crept through the frozen outskirts of our solar system 70,000 years ago, unseen by any living eye, unrecorded by any human hand. It arrived from the direction of the constellation Monoceros, the unicorn, and it departed without ceremony, fading into the blackness from which it came. Its passage through the Oort Cloud lasted perhaps a few tens of thousands of years, a brief encounter by the standards of cosmic time. Then it was gone. But it was not nothing. Scholz's star proved that the borders of our solar system are not sealed. It proved that the comets in the Oort Cloud, those ancient frozen messengers from the birth of the sun, can be shaken loose by the gravity of passing stars. It proved that our solar system is not a fortress. It is a harbour open to the sea, and the sea is full of drifting ships whose courses we can barely chart. We live in a solar system that has been visited before. We live on a planet that has been shaped by those visits, subtly, incrementally, over billions of years, but shaped nonetheless. The water in our oceans may carry molecules delivered by comets that were once residents of the Oort Cloud, dislodged by stellar flybys long before the Earth had an atmosphere to breathe or oceans to fill. The craters on the Moon, those silent circles of impact frozen in ancient basalt, record collisions that may trace back to perturbations caused by stars whose light has long since faded from our sky. We are products of a dynamic cosmos, a cosmos in which stars wander, comets fall, and worlds are shaped by forces that arrive from distances beyond imagination and leave consequences that persist for billions of years. There is a quietness to this truth that makes it easy to ignore. No alarm sounded when Scholz's star passed. No comet struck the Earth. No wave of destruction swept across the continents. The event was, by all immediate and measurable standards, inconsequential, and yet it was consequential in the deepest possible sense. Because it revealed a pattern of repeated intrusion, of ongoing perturbation, of perpetual vulnerability, a pattern that stretches across the entire 4.6 billion year history of the solar system and forward into a future we cannot predict with certainty. The galaxy is not empty space between stars. It is a web of trajectories, a lattice of orbits, a vast and intricate choreography in which every star influences every other star through the patient, invisible force of gravity. Our Sun is not exempt from this dance. It is a participant, moving through the galaxy at roughly 220 kilometers per second, orbiting the galactic center on a journey that takes roughly 230 million years to complete. Along the way, it passes through regions of varying stellar density, encountering stars that drift near, linger briefly in its gravitational sphere, and then recede into the distance. Some of those encounters are distant and gravitationally insignificant. Some of them, like Scholz's star, are close enough to touch the outermost edges of our home, and some of them, in the fullness of geological time, may be close enough to change the course of life on our planet. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We arise from cosmic processes we did not choose, exist within cosmic structures we did not build, and face cosmic risks we did not invite. The Oort Cloud was here before us. The wandering stars were moving before us. The comets were falling before us. We arrived late to a performance that has been running for billions of years, and we will leave long before it ends. But for this brief moment, this cosmically insignificant yet humanly precious moment, we are here, we are watching, we are measuring, we are understanding. Scholz's star is now roughly 22 light-years away, drifting ever deeper into the galaxy, moving toward future encounters with other star systems, other Oort clouds, other repositories of ancient ice. It will pass through other neighborhoods. It will stir other comets. It will leave other traces. And it will do all of this in the same silence with which it visited us, unannounced, unperceived, unremembered by anyone or anything, except by species like ours. Species that have learned through millennia of effort and observation to read the language of light and motion and gravity. Species that can look at a faint smudge on a photographic plate and say, with confidence and wonder, you were here. The Oort cloud stretches out in every direction from the sun, a sphere of ice and silence, 4.6 billion years old, cold beyond comprehension, vast beyond visualization. It is the outermost expression of the sun's gravitational reach, the last and thinnest thread connecting our star to its dominion. Beyond it, there is nothing that belongs to us. Beyond it, there is only the interstellar medium, the near vacuum between the stars, thin and dark and measureless. And it is from beyond that boundary, from that vast and starlit emptiness, that the visitors come. They come slowly, silently, invisibly. They come on timescales that dwarf human history, on trajectories that span the width of the galaxy, guided by gravitational forces that have been accumulating since the Milky Way itself was young. We cannot stop them. We can only watch for them and try to understand what their visits mean. 70,000 years ago, one of those visitors grazed our solar system. It was small and dim and fast. It left quietly, without disturbing the inner planets, without sending any visible comet cascading into our sky. And now, 700 centuries later, we have found it. We have traced its path. We have measured its distance. We have estimated its mass. We have modeled its influence. And in doing all of this, we have learned something essential about ourselves. We have learned that we are not observers of the cosmos, standing apart from it, looking in through a window. We are inside it. We are part of it. It is part of us. The comets that fall from the Oort cloud carry the same hydrogen and oxygen that flow through our veins. The stars that wander through our neighborhood are made of the same elements that built our bones. The gravity that holds the comets in their fragile orbits around the sun is the same gravity that holds our feet to the ground and our planet in its path. We are not separate from the story of Scholz's star. We are a chapter in it, and the story is not over. It will never be over, not as long as there are stars to wander, and comets to fall, and planets to receive what the cosmos sends. The next visitor is out there, somewhere in the dark, moving toward us at a speed we have not yet measured, on a trajectory we have not yet traced. It may be 1 million years away. It may be 10 million. It may already be inside the Oort Cloud, too faint to detect, too small to notice, stirring the ancient comets with a gravity so gentle that the consequences will not be for ages. But it is coming. They are always coming, and the sky above us, calm and still and full of ancient light, is not as peaceful as it looks. Beneath the quiet, beneath the beauty, beneath the steady light of constellations we have named and mapped and loved, the machinery of the cosmos is turning, slowly, patiently, ceaselessly, and it does not wait for us to notice.